Greetings. Welcome to today's session. If you recall where we stopped yesterday, we were looking at analysis of steady state error, right? Just from a big picture perspective, like if you look at the problem of control system design, we when we are designing controllers, we need to ensure the stability of the closed loop system and the performance, right? So the stability of the closed loop system is something which we ensure by looking at the location of the closed loop poles and ascertaining that all closed loop poles lie in the left of the system, right? Now, as far as performance is concerned, once again there are two performance characteristics that we are interested in: the transient performance and also the steady state performance. Okay, if we were to go a little bit finer. So we had quantified transient performance, right, using parameters such as rise time, uh, peak overshoot, peak time, time constant, settling time, and so on, right? So those are actually quantified, like how fast the system is and how the system responds as its response varies with time, right? Once an input is given. On the other hand, the steady state response has to do with this, right? So yesterday we were looking at, the response uh, to a, let's say, a step input, right? So let's say this is our reference step input. It can so happen that the output which is generated may essentially go like this and settle down with a finite steady state error, right? So as we realized, if we have a type 0 system, okay, if the open loop transfer function is of type 0, then there may be a non-zero steady state error even as time t tends to infinity, right? So this is about steady state response, right? So the question that we are asking is that, like, how can we analyze, like a closed loop system and get some measures, okay, or ideas, like about how well the closed loop system that has been designed would be able to track certain reference inputs. Okay, so that is what we are interested in as part of this discussion. So in the previous class, what we did was that, like, we consider the step reference input, and we saw that when we provided the step reference input, if we had the open loop transfer function corresponding to a type 0 system, then there will be a finite uh, non-zero steady state error, right? While tracking the step reference input, and that is 1 by 1 plus k naught, where k naught is the open loop gain. On the other hand, if we had an integral term in the open loop transfer function, then we are assured that the error will converge to 0, okay, as t tends to infinity. Or in other words, for type 1 systems and higher, the steady state error while tracking step reference input would be 0. Okay, so that's something which we observed in yesterday's session. Okay, so today we are going to build on this, and then, like, we look at what happens when we track other types of input. Okay, so the second, what to say, reference input that we will be considering, it will be a unit RAM reference input. Okay, we'll just see what happens in these cases. Okay, so if we have a unit ramp reference input, R of t will be equal to t. So consequently, R of s will be equal to 1 by s squared. Okay, so Now, uh, this will imply that the steady state error, okay, ESL, which will be equal to limit S tending to 0, uh, S times R of S divided by 1 plus G of S, H of S. Okay, so that's going to be equal to limit S tending to 0, S times 1 by S square divided by 1 plus G of S, H of S. Okay, so immediately what do we have? We have one S cancelling in the numerator and the denominator. So consequently, we would have just to simplify to limit S tending to 0, 1 divided by S plus S times D of S H of S. I'm sure all of us will agree, right? So the 1 by S, I take it to the denominator, and that S multiplies the denominator factor, right? So, but then, however, if I apply this limit in the denominator as S tends to 0, I will just be left with this limit S tending to 0, G of S is 1 by D of S, right? Because the first term, F anyway will tend to 0, right? So I'm just left with, okay? So this leads to the definition of what is called as a static velocity error constant, KVE, and that's defined as limit S tending to 0, S times G of S, H of S. Okay, so this is a definition. Okay, so immediately what will happen is that the steady state error, while we are tracking a unit ramp input, okay, will be just 1 by kV. Okay, so this is what will happen when we are tracking a unit ramp reference. Okay, the steady state error is going to be 1 divided by k. Okay, I hope this analysis is clear. Okay, so if we now look at the type of the system, okay, so please note that the type is what I say quantified by the value of capital N, right? So if we go back and look at the open loop transfer function, please recall that the open loop transfer function is going to be k naught t1s plus 1 all the way till tms plus 1 divided by s power capital N TA plus TAS plus 1 times TPS plus 1. Right? So consequently, please note that the type of the system is quantified by the value of capital N. Okay, so that's something which we need to remember. Now, if we have this, and for various types, we want to figure out what is the value of KVE and the corresponding steady state error when tracking a ramp reference input. Okay, we will get this. Okay, so let's calculate this, right? So let's take a type 0 system. So capital N is 0. So what do you think will happen when we multiply the open loop transfer function with S and take the limit S tending to 0? Let me go up here. Okay. So for a type 0 system, so for a type 0 system, there is no S term in the denominator, right? So I multiply by S, okay, and substitute S equals 0. What will happen to S times G of S H of S as S tends to 0? So picturize it, there is no S term, right? Because capital N is 0, right? So you just multiply through it with S and substitute S equals 0. What will happen to S times G of S H of S as S tends to 0?
0.
It will go to 0, right? Because all the other terms, the first order terms will vanish, right? And they will essentially have 1. But we are multiplying by S, right? So consequently, KVE will become 0, right? So consequently, what can we say about the error for a ramp input is 1 by kV, right? So what can we say? Error is going to become
infinity.
infinity, right? So that means that for a type 0 system, right, tracking a ramp signal, right, is not possible, right, even with finite steady state error. So we are going to have infinite steady state error. Okay, as we please note that we are talking about steady state performance, right? What happens as time keeps on increasing, right? So that is what we are interested. So that is point number one. So now, if we go to a type 1 system, let's look at it once again, right? So for a type 1 system, that if we look at G of S, H of S, now capital N is 1. So we have a S term in the denominator, right? Now I multiply by S, what will happen to G, S times G of S, H of S? The S and the 1 by S will cancel off, right? Now if I substitute S equals 0, what will I get? For a type 1 system,
Should be 1.
it will be k naught, right? Because there is
Sorry,
a
K.
k naught term, right? So yeah.
Yeah.
So in other words, if I have a type 1 system wherein I have a 1 by S term in the open loop transfer function, I multiply by S, the S and S cancel off, right? So to illustrate it better, so if you have a type 1 system, right, what will happen? G of S, H of S will be K naught, just to illustrate it, right? K naught T n S plus 1 times T n S plus 1, right, divided by S, okay? TAS plus 1 all the way till TPS plus 1, right? So that's what will happen. Now, if I multiply by S, what's going to happen? Sorry. Okay, if I multiply this by S, what will happen? This will be S, right? This S and this S will get cancelled. Now, if I take limit S tending to 0 of S times G of S, H of S, what will happen if I substitute S equals 0? I'll be ending up with K naught, right, which is the open loop gain. Okay, so consequently, for type 1 systems, the value of KVE will become 1 K naught, and so the steady state error when we track a ramp input will become 1 by K naught. Okay, so that is what we will have. Okay, so please, so what is the point? If we have a type 1 system, we will get a finite steady state error while tracking a ramp input with a what is it, with the steady state error being 1 by K naught, okay, where K naught is the open loop gain, right? So higher the open loop gain, smaller will be there. But however, increasing the open loop gain will have its own consequences. It will increase the effort that the controller needs to provide as well. Okay, amongst other things. Okay, so that's something where there is a tail. All right. So that is one. So now, if you go to type 2 systems, what do you think will happen? I'm going to essentially do it here itself so that like I save some space. Okay, so please note what I am doing. Okay, I'm just changing this. Okay, so for a type 2 system, what's going to happen is that I'm going to have a S squared term, right? So when I take S times the G of S, H of S, I'll just cancel this off, right? And now if I substitute S equals 0, what will happen? I will get KVE to be infinity, right? So as a result, the static velocity error constant will be KVE will be infinity, and then consequently the steady state error to track, which we will get while tracking this unit ramp reference input will be 0. Okay, so What does this mean? This implies that if we wish to track a unit ramp reference input with zero steady state error, then the open loop transfer function must be type 2 or higher. Okay, so now you can see the correlation, right? So when we wanted to track a step input, right? We wanted the open loop transfer function to be type 1 or higher. Okay, now if you want to track a ramp input, like the open loop transfer function should be type 2 or higher. Okay, so that is those are some observations that we can make. However, see, what we should remember one thing, that is, what is it? What is this? What is the important thing here? The important thing to know is that, yes, we can keep on adding integral terms, okay, to the open loop transfer function, right? What do I mean by integral terms? That is adding, including this 1 by s terms in the open loop transfer function, right? And it keep on increasing the type of the system. However, please note that if I have a type 2 system, I am going to have two open loop poles at the origin, okay? Then in fact, stabilizing the closed loop system itself will be, what to say, difficult. So, if I have two type 2, this will imply two open loop poles at the origin. Okay? So, then stabilizing the closed loop system itself will become challenging. Okay? So, of course, this entire analysis of the steady state error is built upon the premise that we are able to stabilize the closed loop system, right? Was it not? See, the initial assumption with which we started off is that we wanted we essentially had the closed loop system as stable, and then we are building all the arguments based on that, right? So that's what we are doing, right? Now the point is, yes, we are deriving some condition, but however, if we want a certain type of a system, right? As per our definition in this discussion, if you want type 2, the number of open loop poles at the origin will be 2, and then stabilizing such a system is also challenging in the first place. So that's something we should keep in mind. All right. So yeah, any questions on the steady state error analysis with the unit ramp reference input? So now moving forward, next we consider a unit parabolic reference input. Okay, so what is this unit parabolic reference input? It will be R of t will be equal to t squared by 2. Okay, so you can see that that's like a parabola. So R of s will be 1 by s cube. Okay, so now we do the same thing, similar thing again, right? So we do the similar analysis. So then the steady state will be equal to limit s tending to 0, s times R of s divided by 1 plus g of s h of s, which is going to be equal to limit s tending to 0, s times 1 by s cube divided by 1 plus g of s h of s. So what will we have? We'll have one, this s cancel off this one of the s in the s cube term. So we left it s square, right? Is it not? So what will happen is that this will get a limit s tending to 0, 1 divided by s square plus s square g of s h of s Now, if we substitute s equals 0, what will happen is that we are going to have limit 1 to s tending to 0, 1 by s square times d of s. Okay, so that's what we are going to get. Okay, so once we get this, okay, so we define what is called as a static acceleration error constant. Okay, KAE, which is defined as limit s tending to 0, s square times g of s. Okay, so that is the static acceleration error constant. So as a result, we have a parabolic reference input. The steady state error is going to be 1 divided by k. Okay, so that's what we have. Okay, so that's what we have. So we do a similar analysis, right? So what will be the, for the type of the system, what will be the value of KE, and consequently, what is the steady state error? Okay, so in this case, for a parabolic. Now I request you to help me, right? So let's say we consider, let's say type 0 system. What do you think will happen? In a type 0 system, you multiply the open loop transfer function by s square, right? And then you essentially take limit s tending to 0. What do you think is going to happen? So type 0 means we are going to have this, right? Okay, so we are
It
going to
will
have
become 0.
to become 0, right? Good. So this is what we are going to have, right? So there is no s for initially is there in the gen form, but when capital N is 0, the type is quantified by n, right? Is it not? When capital N is 0, this term goes away. Now we multiply this by s squared, right? So what, and then I substitute s equals 0. What will happen is the following: I will get KAE to be 0 and the steady state error to be infinity, right? When you're tracking a parabolic reference input, right? So I hope this is clear to everyone. All right. So now, if I have a type 1 system, what is going to happen? If I have a type 1 system, I'll have a s term in the denominator, right, of the open loop transfer function. And now I multiply by s squared. If I multiply by s squared, what is going to happen? I'll have one s and one s cancelling off, but still in s squared g of s, I'll have a s term in the numerator. So now when I substitute s equals 0, still I will have ke to be
0.
0, right? So consequently, the steady state error for a unit parabolic reference input is one to be infinity, right? So the point is, if we want to track a unit parabolic reference input, suppose, let us say, then a type 0 and a type 1 system will not be enough to get a 0 steady state error, right? So they are going to result in infinite steady state error, okay? So that's something which we need to remember. Now, if we look at a type 2 system means I will have s squared in the denominator, right? Now, this s squared and s squared will cancel off. So what will I get for ke? I will get
K naught.
k naught, right? I will get k naught. Good. So if I get k naught, the reciprocal of that will be the steady state error. So I will have 1 by k naught, right, as the steady state error. Okay. So now moving ahead, if I have a type 3 system or higher, what will happen is that, like, I will be able to cancel off this s square. Let's say we consider type, what to say, type 3 system. I will be able to cancel off s squared with s squared in the denominator, and still be left with a s in the denominator, right? And then I take the what is the limit extending to 0, then I will get k to be infinity, and the steady state error to be 0, right? So consequently, what is it that we can observe immediately? If we want to track a parabolic input, then we require type 3 or higher. Okay, if you want to track a parabolic input with zero steady state, okay, that is key. Okay, so we require type 3 or higher system. Okay, to track unit parabolic reference with zero steady state. Okay, that's very important. Okay, unit parabolic reference input with zero steady state error. Okay, of course, as we already discussed, like yes, I can anyway keep on introducing these yes terms in the denominator, but however, please note that the more one by s or integral terms I keep on introducing in the denominator, the the original problem of stabilizing the closed loop system itself will be difficult. Okay, so that should be kept in mind. Okay, so because if we have a type 3 system, that means we are having 3 zeros at the origin. Okay, for the open loop system. Okay, or three, sorry, not 3 zeros, 3 poles at the origin, right, for the open loop system. Okay, so that's going to become that's going to make things very challenging, like as far as stabilizing the closed loop system is concerned. Okay, so we should be aware of it. Okay, when we are trying to design it. All right. So I hope this discussion on steady state error is clear. Okay. So
Yes,
any questions?
yes, sir. One question. This t square by two you have taken so that two terms can be considered.
Yeah. So that's a standard signal. Okay, for a unit parabolic reference input, so that you will get the Laplace transform as 1 by s cube. Okay, that's it. Okay.
Okay, sir.
Okay.
See,
Yeah.
sir, unit parabolic means like t square means parabolic. But what is unit here, sir?
Well, unit parabolic, essentially, you want to ensure that when you want to take the Laplace transform, you will get a 1 by s cube. It's used in that.
Okay, sir. Thank you.
Okay. Okay. So, any uh, other questions on the steady state error analysis? Okay. Now what we are going to do is that, like, we are going to move on to this next topic. Okay. And we will essentially see, what essentially we have. We can learn, right, further on as far as the control design process is concerned. This is something which you will use further on when you do your projects and so on. Okay, so the next topic, which I just going to motivate today, is what is called as a root locus. Okay, so what is this root locus? So let me motivate what this is, and then like we will discuss it later, right? So we'll discuss it in the upcoming class. Okay, we learn what to do. So now I'm just going back to our discussions from a few lectures before, where let's say we identified this area, right, in the S plane, where we want our closed loop poles to lie, right? When to satisfy both stability and performance. So now the point is the following. Okay, so if we look at this particular region, okay, in the left of complex plane, what will happen is the following. Right? So if we essentially take this particular sub-region, okay, if we ensure that all our closed loop poles lie in this red shaded region, okay, in this plot, we ensure that we satisfy closed loop system stability and performance. Right? So now the question becomes the following. Right? The question is, can we have a design tool, like which will essentially ensure that, if I am able to plot the variation of the closed loop poles as a system parameter. Let us say I'm designing a proportional controller. Okay, so the proportional controller gain is my system parameter. Suppose if I am able to plot the variation of the closed loop poles as we vary the system parameter, which in this case is proportional gain, I may be able to find out for what range of proportional gain all my closed loop poles will be in this red shaded region. Okay. Then like such a design tool would be very useful to me, right? So if I am able to graphically visualize, like what is the range or what are the ranges of KT, or the proportional gain that will get all my closed loop poles in this red shaded region, then I'm done, right? Because I would be then able to design and tell the designer that, look, the proportional gain in the range, and then you'll be able to satisfy both stability and performance. Okay, and that is exactly what we get by root locus. Okay, so as the name suggests, the root locus is the locus is a graphical representation. It is the locus of closed loop code. Okay, the way we apply it, in general, if you look at it, it is a locus of roots of a polynomial as you vary a system or a polynomial parameter. But in our context, okay, we are essentially saying that like it is the locus of the closed loop pole as we vary a system parameter. The system parameter can be a controller parameter, for example. Okay, so that is what we essentially get by a root locus. Okay, so let me explain what this is. Okay, so as we already have discussed, we can draw the closed loop, what to say, block diagram in this way. Okay, where we have combined the plant transfer function and the controller transfer function into G of S, right? And then like we have this as the standard block diagram for the closed loop control system, right, with negative feedback. Okay, so please remember that the closed loop transfer function is going to be equal to G of S divided by 1 plus G of S. Okay, so now typically, like of course, this our argument of root locus is essentially visualized graphically, and we consider uh, that the open loop transfer function. Okay, so if you look at the open loop transfer function, G of S, H of S. Okay, so we consider that the open loop transfer function G of S, H of S can be expressed as, okay, so this is a premise once again. We want to express the open loop transfer function in this form, G of S, H of S to be equal to some K times S plus Z1 times S plus Z2 all the way till S plus Zm. Okay, divided by S plus P1, S plus P2, all the way till S plus Pn. Alright. So in this particular representation, we can immediately see that the open loop zeros are at minus Z1, minus Z2, all the way till minus Zn. Okay, open loop poles are at minus P1, minus P2, all the way till minus Pn. Okay, so these are the open loop poles and open loop zero. Okay, so suppose if we are able to, we will also see why we are looking at the open loop transfer function. Okay, next. Okay, so why are we focusing that by analyzing the closed loop characteristic polynomial? Suppose let's say of course here k is a real number. Okay, suppose we are able to represent the open loop transfer function in this form, where minus z1 through minus zm are the open loop zeros and minus p1 through minus pn are the open loop poles. The question that we are going to ask ourselves is the following, right? How do the closed loop pole vary as the parameter k is changed? Okay, so that is what we want to ask, and that is the root loop. So now I am sure we can correlate it to the definition that we wrote about, right? So that is like we want to essentially figure out what would be the locus of the closed loop pole as the various system parameters. So the system parameter is this parameter k. Okay, most likely it will be a controller parameter, or it will be a function of the controller parameter. So the question that we are asking is that, okay, so if we have this, then what we are going to have is the following. We essentially what to say are going to have this particular locus, of the closed loop poles as we vary this parameter k. Then the question that we ask is that what is that sort of graphical visualization called as? Okay, and that is what is the root locus. So we will be looking more at root locus as we proceed in the next few lectures, so that we can learn how to use it as a design tool. Okay, so the main what to say advantage is that, as we just discussed, if we identify a sub-region in the Nassau complex line where we need to place all the closed loop poles to achieve closed loop stability and performance, root locus will help us, in figuring out for what ranges of these system parameters, which in this case is k, would I be able to place all my closed loop poles in that region. Okay, so that is where we are going to apply the technique of root loop. Okay, so we will discuss further, okay, as we go along, and then we will essentially also see why we are looking at the open loop transfer function. Okay, so that's something which is important, right? Because one may wonder that we want to look at the closed loop transfer function, right? Isn't it? Because we are looking at the closed loop pole. So when somebody is looking at the closed loop pole, why would they want to consider the open loop transfer function? So we will figure out the reasons for that also, okay, as we go along, right? So I just wanted to briefly introduce the notion of root locus and motivate its application, and we will learn the steps for constructing the root locus as we go further. All right, okay. So any questions on this? Okay. So if not, before I close today's session, I would like to draw your attention to the fact that homework 2 has been posted. So what to say, in this homework 2, the first task is for you to derive the governing equations of the system. It's a very simplified representation of the DC motor. So please derive the governing equation and then get the transfer function of the DC motor, taking theta as the output and V as the input. Okay. So then what you do is that like you are given these system parameters. What you need to do is that like you need to design a unity negative feedback closed loop control system with using a proportional controller, and you have to essentially determine the range of proportional gain KP for which the system would be closed loop system would be stable, and also it has a maximum peak equals to less than 10%. So that is your homework number 2. So please start working on your homework, and if you have any questions, we can discuss them subsequently. Okay, you have time to do the homework. All right. Okay. So please look at this problem and start thinking about the solution. All right. Okay. So any questions on this homework? No? All right. So if not, I will close the lecture here today, and then like we will continue in the next class. Okay? Thank you.